Good evening, everyone. My name is Sridhar, and I am from Computer Science and Engineering Department. And for AAT Tech Talk, my topic on mathematics for computing is intermittent discrete observation control for synchronization of stochastic neural networks. Introduction to neural network synchronization. Neural networks are computational models inspired by biological neural systems. Synchronization of neural networks is vital for coordinating the information processing. This presentation explores intermittent discrete observation control in stochastic neural networks. And also we can see here the neural networks are the computational models which are inspired by the biological neural systems as we are having in our body. There are like many neural systems which are passing through our brain to every part of our body. The neural networks also is inspired from these biological neural network systems and as a computational models. So, synchronization of neural networks is for vital for coordinated information processing. This presentation explores the information of the intermittent discrete observation control of stochastic neural networks. Background and motivation. Traditional control methods often require continuous monitoring, which can be resource intensive. Intermittent observations reduce communication and computational load. Ensuring synchronization under these constraints is a significant challenge in a neural network control. Here, the background and motivation of these neural network systems are traditional control methods are often require continuous monitoring and also you're having the intermittent observation which also reduces the communication and computational load and also ensuring synchronization under these all the constraint is a significant challenge in neural network control. Stochastic neural network overview. Stochastic neural network incorporate randomness to model uncertainty and variability. They are used in applications like pattern recognition, decision making, and biological modeling. Stochasticity complicates the analysis and control of network dynamics. Here we can see here the stochastic neural networks incorporate randomness to model the uncertainty variability. They're also used in applications like pattern recognition, decision making, and biological modeling. Synchronization in neural networks. Synchronization refers to the alignment of states or output across different network nodes. Achieving synchronization enhances the robustness and functionality of neural net systems. Various factors including noise and delays affect the synchronization performance. Here we can see the things which affects the synchronization is achieving various factors including noise and delays which affects the synchronization performance and also synchronization is nothing but the alignment of states or outputs across a different network nodes. Discrete observation control concept. Discrete observation control involves monitoring network states at specific time instance. This approach constrains with continuous observations, saving resources, and also it enables practical implementation in large scale and or resource constrained systems. Here we can see a discrete observation control system concept where the discrete information control involves the monitoring of network states at any specific instant of a time and also these approaches are the saving the resources and continuous observation. Intermittent observation strategy. Intermittent observation entails observing the network at non-uniform scheduled time intervals. The interval can be periodic or event triggered based on system states. Proper scheduling is crucial for maintaining desired synchronization levels. And also, we can see here the intermittent observation strategies are very essential for the entailing the networks and also a non-uniform scheduled intervals. The intervals can be the periodic or event triggered based on the system states. It also proper scheduling is crucial for maintaining desired synchronization levels. Challenges in control design. There are many challenges in control design where limited observations can lead to information gaps where the complicating control strategies. Noise and stochastic disturbances impact the effectiveness of intermittent control. Designing robust controllers require accounting of for randomness and observation constant. Here we can see some of the challenges in control design. There are limited observations can lead to the information gaps and also complicating the control strategies. And also the stochastic and the noise disturbances impacts the effectiveness of intermittent control. And also designing these all robust controllers requires a accounting of randomness and also the constant observation of constant. Mathematical modeling of a neural networks. The dynamics are often modeled using stochastic differential equations, which are also known as SDEs. These equations incorporate deterministic and stochastic components. Proper modeling is essential for analyzing synchronization under intermittent observation. Here we can see the dynamics which are often used in the models such as stochastic differential equations, and also these equations incorporate deterministic stochastic components, and also proper modeling is essential for analyzing synchronization and also under these intermittent observations. Control framework for synchronization. Here, the control framework combines feedback loss with intermittent observation schemes. Lyapunov functions are typically used to analyze stability and convergence. The goal is to design controllers that ensure synchronization despite stochasticity and observation gaps. You can see here the control framework for synchronization are the control frameworks combines the feedback loss, and also intermittent observation schemes. And also we use some functions like Lyapunov functions, which are typically used to analyze the stability and convergence of these functions. And also these control framework for synchronization. Main result and theoretical contribution. There are the this is we are now discussing about the main results and also the theoretical contributions for these neural networks, where the paper establishes sufficient conditions for mean square synchronization. It introduces Lyapunov based criteria that accommodate intermittent observations. The result provide guidelines for selecting observation intervals and control gains. Here we can see uh, the paper establishes a sufficient condition, which are also known as the mean square synchronization, and also it introduces Lyapunov based criteria, which is also known as considered as the function where the Lyapunov is a function where you can use to accommodate intermittent observations. These results provide as a guidelines for selecting the observation intervals and control gains. Simulation studies and validation. Here, the numerical simulation demonstrate the effectiveness of the control strategies, where and the different observation intervals and noise levels are tested to assess robustness. Results confirm that synchronization can be achieved under practical constraints, where we can see here the numerical simulations are the simulation studies and the validations, where you can also have the effectiveness and the demonstrate the effectiveness to control the strategies. And also these different intervals and the noise levels are tested to assess the robustness, which is also known as the clear also gives a clear image of neural networks, which results in the confirmation of the synchronization and can be achieved under practical constraints. Now let us discuss about the practical application and implications, where such control schemes are relevant in sensor network, brain modeling, and distributed computing. Intermittent observation reduces energy consumption in biological and technological systems. The approach supports scalable and resource-efficient neural network management. Here we can see some practical applications such as which are relevant in sensor networks, such control schemes which are relevant for sensor networks, brain modeling, and distributed computing. And also we can see here the intermittent observation reduces energy and consumption in biological and technological systems. The approach supports scalable resource efficient neural network management. Limitations and future directions. There are some current models assume idealized conditions that may not capture all real-world complexities. This is the main limitation for this project, and also extending the framework to heterogeneous or delayed networks remains a challenge. And also, future research could explore adaptive observations, schedules, and learning-based control. Here, these are the limitations and the future directions where the future research can could explore the adaptive observation scheduling by removing these limitations such as uh, current, which are like are not capturing all the real world complexities, and also the frameworks which are heterogeneous or delayed networks, that remains a challenge for us. And the summary and conclusion, the intermittent discrete observation control offers a practical solution for neural network synchronization where the theoretical analysis confirms its effectiveness in stochastic environments. The approach balances the resource constraint with the need for the robust synchronization. And this is all about the this intermittent discrete neural networks. And thank you.